you in good condition today. Yeah. Today is week 14. Yeah. So that we have 1 week left. Yeah. So next week will be the last week for the course. So yeah, we will finish the material today. And actually the material is not much. Yeah. So we will continue our discussion on partial differential equations. Yeah. And if last week we have learned about ODE, yeah, which is about the ordinary differential equations. Now today we are going to talk about PDE. So the difference is that when we have a PDE, yeah, so that it will involve more than one independent variable. Yeah. Okay. So this is the code for today's class. Yeah. And now I will change the screen to the slide. Yeah. So now we are going to continue to part 8, which is about partial differential equations. Yeah. And I think it's not many for today. Yeah. And I think this is quite easy because you have learned of this before as well. Yeah. So you have learned about this as well. In heat transfer. Yeah. So when you learn about heat transfer, you already learn about this. But we will look deeper on this. Okay. Okay, so partial differential equations, yeah, is commonly found in engineering problems. Yeah, for example, if you have the heat transfer problem, in which we have a plate, a two-dimensional plate, for example, like this one, and then we keep, for example, the temperature, yeah, constant at a certain temperature in one and the second side, and also for the bottom and the right side here at the cooler temperature, for example. Yeah, or also we can give, for example, insulation. Yeah, so if, for example, we give an insulation here, so that we can also find the distribution of the temperature for the plate. Yeah. Okay. And also, for example, if we have a case in which we have a dam here, and we have a liquid water here at different heat, so that the potential, yeah, the difference of the heat here, of the level of the fluid here will cause the fluid to flow through the impermeable rock. So this is the rock in which the water can go through to the rock formation, so that it will go to the lower energy side here, which is on the right side. So here we have the flow line, yeah, and we have also the equipotential line. So if we remember when we learned that in fluid mechanics, yeah, we have the streamline and also we have the potential line. Yeah. So this is also the case of partial differential equations. Or for example, here we have a conductor, yeah, and which, for example, this is commonly occur in electromagnetic, for example. So we can also find the potential line as well for the current, yeah, for example, like this one. So we can find the distribution as well here. So that this is the case in which all of these cases considered as partial differential equations. So that when we talk about partial differential equations, so this means that we have a differential equations, we have the derivatives inside the equations, and this involve two or more independent variables. So for example, here we have the Laplace equations here, in which we have the second derivative of a function f to x plus the second derivative of f to y that will be equals to 0. Yeah, so this is called the Laplace equation. So in this case, we have two independent variables, which is x and y. Yeah, so we see here that we have a distribution in space, yeah, in x and y direction. The second we have here is the diffusion equations, in which here we have k, in which k here is the diffusion coefficient. multiplied by the second derivative of f in x direction, that will be equals to the first derivative of f in t direction. Yeah. So here we have two independent variables that are x and t. Yeah. So x here is in spatial direction, in x direction, while t here is usually in time. Yeah, time direction. So we have a time. We have the unsteady term here, yeah, which is del f over del t, unsteady term, and here we have the spatial discretization in x direction. And we have the third example, yeah, which is called the wave equations. Yeah, so this is the wave equations, in which we have two independent variable as well. So we have here on the left side, we have the second derivative of y in x direction, that will be equals to 1 over square c times the second derivative of y in t direction. So here we have also two independent variables of x and t, but we see here that the equation is different. So what we have here on the right-hand side for the unsteady terms is the first derivative, while in the wave equations, we have the right-hand side here, which is the derivative in time here is the second derivative. Yeah, so this is examples of partial differential equations. And when we learn about partial differential equations, we have a classification. Yeah, we have seen these three examples of PDE. Now we will look at for those example, it can be classified into different type of PDE. Yeah, so that when we learn about PDE, it's very important to classify in which type the PDE is. Yeah, so when we have the linear second order PDEs, yeah, so this is very important because this is used in many engineering problems. And why this is very important to classify it, because each category relates to specific engineering problem. Yeah, and different approaches are used to solve these categories. Yeah, so this is very important to understand in which group, yeah, our problems classified into. Okay, so we will see the classification here. So that if we have here a second order linear PDE, in which we have, in this case, two independent variable. Yeah, so in general, we can have the PDE is written in this form. Yeah, so this is the PDE. Yeah. Okay, so we have here, we have A times UXX. So if we look at UXX here, this will be the definition of the second derivatives of U and X direction. Yeah. So if we write it down here, so this will be similar to A del square U over del X squared plus B times del squared U over del X del Y. Yeah, so because we have the derivative in X and Y direction, so that will be UXY, and then plus C times del squared U over del Y squared plus T, that will be equals to 0. Yeah, so that if we have this general form of the PDE, so that now we can classify in which group our case belongs to. Yeah. So for example, before we have the Laplace equations, yeah, in which we have del squared U over del X squared plus del squared U over del Y squared, that will be equals to 0. So that we can see here, we have here, which is the same term. Yeah, and this one is also the same term. So that means we have A is 1 for this case, A is 1, and C is 1 as well. Yeah, so that when you want to find in which problem our in which type our problem belongs to, so that we can check with calculating p squared minus 4ac. Yeah. So when we insert the value of p here, we don't have p, we don't have this term in the equation. So that means p is equal to 0. Yeah, so that 0 minus 4 times AC. A is 1, C is 1. So that it means that we will have the multiplication here, or the calculation of p squared minus 4ac here will be negative. So it means that it will below 0. And if we have this value below 0, it means that we have an elliptic problem. So that if we have these equations, the Laplace equations, so that means this Laplace equations falls into the elliptic problem. Yeah. Okay, so this is the calculation. Yeah, for the same example that I have written there, we have the second derivative of u and x plus the second derivative of u in y direction, that will be equal to 0. So that when we calculate p squared minus 4ac is lower than 0 because negative, so that the Laplace equation is an elliptic equation. Yeah. So this is the first classification. And we also have the heat equation. Yeah, we have the heat equation. And for example, we have 1D heat conduction or unsteady one-dimensional heat conduction in a rod, for example. Yeah, so that we can write it down as alpha. For example, this is the heat conduction, the heat coefficient. Yeah, times the second derivative of u in x direction minus the unsteady term, which is del u over del t. The derivative, the first derivative in time, that will be equals to 0. So when we look at these equations, back again here, so it means that what we have is only the value of A here. Yeah, we have the value of A. Well, the value of C, P and C is 0. Yeah, so that the calculation of p squared minus 4ac, that will be equal to 0. So this means if we have a 1D unsteady one-dimensional unsteady heat conduction, so this means that we have a parabolic problem. And if we have the wave equations, as we seen here, so that we have here, so this will be the value of A. Yeah, so this will be the value of A. And we have here the second derivative in the second independent variable, which is t. So that means this will be c. So the c value will be minus 1. Yeah. So that when we calculate A, which is always positive, and C, which is negative, so that the result here will be always positive. So this means that wave equations is included or classified as an hyperbolic equation. Yeah. So we've seen here that we have 3 different equations in which all of these 3 equations, each of that goes into different type of PDE. Now, this is very important if we want to see the physics, yeah, because when we have, for example, back here, when we have an elliptic equation, for example, in this case, we can use that, for example, for temperature. Yeah. So this will be the 2-dimensional heat conduction, for example, on a plate. Yeah. So if, for example, we have a domain of x and y, yeah, and we have the plate here, and we want to find the temperature distribution in each of the plate here. Yeah, and we want to find the distribution for each of the point inside the plate here. Yeah, so that we can give a boundary condition. Yeah, of course. And then what we can do is that we can discretize this equation so that we have the distribution. Now, when this is included in elliptic, why this is important to understand that this is elliptic problem in the point of numerical view, because we see here when we have an elliptic equation, it means that when we have a disturbance, yeah, when we have a disturbance at one point, for example, at point P here, so what happens? So that this disturbance will be propagated to all area inside the domain. Yeah. So it means then when we have a disturbance at one point here, for example, so that the effect of this disturbance will be occurring for all of the area of the domain. Yeah. So for example, here we give a heat generation in one point here. So of course, the heat generation that we give in the middle here will give effect on the temperature distribution on the other area of the domain. Yeah, so this is included as an elliptic. Yeah, so we have an illustration. Yeah, so if we have an elliptic problem in which we have a case which is included as an elliptic problem, it means that any disturbance, any disturbance which is given in one point of the domain will have effect on all area of the domain. Okay, so we will see next, which is about the parabolic equations. So here, for example, we have the domain which is in x and t, which is t is time, and x here, for example, is the spatial direction. Yeah, so we can imagine this as a 1D conduction in a rod, for example. Yeah, we have this hole that held as temperature 1 and temperature 2, for example, here. So this act as a boundary condition at the end side of the rod here. And then we want to find the temperature distribution inside the rod here. So this will be 1D heat conduction. But then we do the time marching from one time to another time, so that we will see later it will be steady. Yeah. But initially, when the temperature here is low, for example, and we hold the two sides here at higher temperature, so there will be an increase from time to time. Yeah, so there will be an increase of temperature inside the rod from time to time. So this is the case of parabolic equations. So that, for example, here we have x direction. So we have the solution here. This is the solution. Yeah, the domain that we want to find. So that if we want to, for example, give a disturbance at one point P, in which the disturbance here is given at a certain location, which is x0. Yeah, so that we give a disturbance at x0, for example, here. And then this disturbance is given at a time of t0, for example. Yeah, the disturbance is given at time t0. So what happens here when we see the effect of the disturbance that we give into the domain of the solution? So we see here that the disturbance will have effect only on the time after. Yeah, because we do time marching, and if we give a disturbance at one time, for example, at t0, so what will affect it will be the calculation afterwards. Yeah. So what is calculated before, for example, at t minus 1, t minus 2, so this will not be affected by the disturbance that we give. Yeah. So this area will not be affected by the disturbance that we give. So that when we have a parabolic equation, so we can see here that we have the domain of dependence, yeah, domain of dependence, and we have the domain of influence. Yeah. So it means that what happens here, that when we give a disturbance at point P, so that the calculation that will be affected will be all of the area on X. So that will be affected all, that will affect all the area, yeah, or all points in X direction here. But this only affect the calculation after the disturbance being given. Yeah. And what is before that? Yeah. So the domain before that will be domain of dependence. Yeah, domain of dependence. It means that what happens after here is depend on this one. Yeah. So what will be the effect later at the time step after here? So that will be caused by that will be determined by the domain of dependence and also the disturbance that is given. Yeah. So this is the illustration of the parabolic equation. Next result we have wave equations. Yeah, and this is included as parabolic equations. So how is the illustration for parabolic hyperbolic equations? Yeah, so again we see here we have the same independent variable, which is x and t. So it means that we have 1D as well, yeah, 1D distribution, and also we have a time marching here. But the difference is that the physical meaning, yeah, is different. Yeah. So for example, here we have a point P. Yeah, we have a disturbance which is given at point x0 and t0. So that what will be affected by the disturbance that we give here. So we see here that the domain that will be influenced, yeah, or affected by the disturbance that we give is in this area. Yeah. So we see here that there is a big difference between parabolic and hyperbolic, yeah, because in parabolic, if we give disturbance at one point here, so that all of the area here, yeah, all of the points here will be affected as well by the disturbance that we give. But if we look at the hyperbolic equation, it means that when we give the disturbance at this point, so that the other point will not directly affect it. So the area, yeah, the area that will be affected by the disturbance that we give is only small area close to the point x0. What about the point which is far away from point x0, so that will not be affected by the disturbance that we give? And also, how is this calculation, the solution of the time step after we give the disturbance? So that will depends on the domain of the dependence here. And the domain of dependence is not for all of the domain here, but it's only small area close to the point of x0. Yeah, so we see here that for each of this PDE here has different physical meaning. Yeah, has different physical meaning. Okay, so that because we have three topics here for numerical analysis this time, we will limit only in elliptic equations. Yeah, so this will be the focus. Later, if you want to do undergraduate study, you will learn about parabolic as well, yeah, and also hyperbolic as well. So, yeah, you can see here that PDE here, partial differential equation, is the basis of finite element method. Yeah, so if you're interested in, for example, doing structural analysis for your final project, for example, yeah, because I think you're already in the 5th semester, yeah, at the moment, yeah. So you might have, you might need to, yeah, have a direction, yeah, for example, on which area you are interested into to do your final project later, yeah. So if you are interested to do structural analysis, for example, yeah, like finding the forces or the stresses, yeah, in a structure. So that will be using finite element analysis. So the basis of finite element analysis is also based on PDE, yeah. And also, if you are interested in fluid mechanics, for example, and you want to do simulation using CFD or computational fluid dynamics, yeah, so that you will also utilize this one. Yeah, so basically what we are learning today is the basis for finite element method and CFD. And you will learn later, for example, in CFD that the equation is a mix, yeah, between elliptic, parabolic, and hyperbolic equations. Yeah, so that later when you go further, you will get a more complex equations. Yeah, but in general, this is a basis. So if you understand this one, yeah, so you already have a basic step for you to continue to finite element method and computational fluid dynamics. Yeah. Okay, so that here we will learn the elliptic problem first, yeah. But before that, we will look the requirement for PDE, yeah. So if we want to have a solution to a PDE, which is a partial differential equations, it means that we need boundary conditions. Yeah. So if we don't give a boundary condition, it means that we will have no unique solution. Yeah. So for example, if we have only this equation, so there are many solutions that will satisfy this equation. Yeah. So that to have a unique solution, we have to provide the boundary condition. Okay. So what are the boundary condition that we can give in this case? Yeah. It depends on the type of the BDE. Yeah. For example, here we have the second derivative of u in x direction. So it means that if we have a second derivative, it means that we need two boundary conditions to define this one. Yeah, two boundary condition. And we have here another term, which is u in t. Yeah, the derivative of u, the first derivative of u in time. Yeah, it means that we need additional boundary condition in t direction. Yeah, so it means that we need two boundary condition in x direction, and we need one boundary condition in t direction. Yeah, wait a moment. Yeah. So because we have the second derivative in x, it means that we need two boundary condition in x direction. So we take two here, which is at x0. Yeah. So this is a two boundary condition that we have, which is here x at 0, and this is x at 1. Yeah. Put it here, x is 0 and x is 1. So here we have the u value is 0. So that here the u value is 0 at this point. Yeah, and this is for all time. So it means that along this line. So this is the first boundary condition. And we have here u, which is equals to 0 at x equals to 0 for all time. So this is the second boundary condition. Yeah, the second boundary condition. And then we have u for all x at t equals to 0. So that if we have t here is equal to 0, yeah, at this point we have t equals to 0 for all x. So that means we have this, yeah. So that will be sinus pi x. Yeah, sinus pi x. Yeah, so that it means that we will have this sort of distribution. Yeah, we have this profile for u. So this is the profile of u, which is sinus pi x. Yeah, for example, like that. So this will be two boundary condition. And this one is also two boundary condition in x direction. Yeah. And we have one boundary condition here in t direction. Now, because this is in time, so commonly this is called as initial value. Initial value. Yeah, so we have initial condition. Sorry, initial condition. Yeah, so this is called the initial condition because this is in time. Yeah, when we have a time, so that is called also initial condition. But basically, these three are the boundary. Yeah, so this is bounded the solution so that we will have a unique solution for the area inside. Yeah, so we have a unique distribution. Okay. So how to get the solution for this? Yeah, I think you have learned of this as well in heat transfer. So analytic solutions are possible for simple and spatial or ideal case only. So that here together to get a solution, we will use the finite difference method. Yeah. So finite difference method similar to the ODE that we have learned last week. So that we will use the central divided difference. Yeah. So central divided difference are substituted for the partial derivative in the original equations. So that here we will have a partial differential equation will be transformed into a set of linear algebra equations. So that when we have the matrix constructed, so that we can solve it with the iterative method or the LU decomposition method and so on. Okay, so we will look at it again here in the central divided difference. So that if we have del f over del x, which is the first derivative in x, so that will be equals to fi plus 1j minus fi minus 1j over 2 times delta x. Now, because we talk about PDE, so that we have two independent variables. In ODE before, when we learn about boundary value problem, we have only in x direction. Now in PDE, we have two independent variables. The next one is in y direction. So that we can extend in 2-dimension grid like this one. Yeah. So that we have, we give a notation at the point. At the point itself, it will be ij. At the point on the east side, yeah, so the east side or the right side, the east side here is I plus 1j. And on the left side here or the west side, we have I minus 1j. And we have on the north side, yeah, or the upper point here, we have ij plus 1. And for the south side, we have ij minus 1. Yeah. So that here we will have a dependency of the temperature here, for example, or the function value here depends on the value of the neighboring nodes. Yeah. So that the first derivative using central divided difference, so that will be I plus 1, fi plus 1j minus fi minus 1j divided by the distance, which is 2 times delta x. The second derivative will be fi plus 1 minus 2 times fij plus fi minus 1j divided by square delta x. Again, in this y direction will be similar. Yeah, so the first derivative in y direction will be fij plus 1 minus fij minus 1 divided by the distance, which is 2 times delta y. And the second derivative of f in y direction, that will be fij plus 1 minus 2 times fij plus fij minus 1 divided by square delta y. Yeah, so this is the central divided difference that we can use to substitute the derivatives that appear in the elliptic equations. Yeah, so this is again about the elliptic equations. So that we have the value of p squared minus 4ac is lower than 0, so that is included in elliptic equations. The example here is the steady state distribution of heat in a body. So this is the test case that we will use in the study. Yeah, so you can see this is slightly overlapped to what you have learned in heat transfer. And then studying the steady state distribution of electric charge in the body. Yeah. So this is also Laplace equation. So similarly, yeah. So the equation is similar. So that we have here, for example, we have steady state distribution heat in two-dimensional body, for example, like this one, we have the second derivative of t and x plus the second derivative of t and y, that will be equals to fxy, in which this is the source term. And this source terms, because we talk about temperature, so this can be the heat source of the heat sink. If the heat source, so that will be positive. If the heat sink, so that will be negative. Yeah. Okay. And T here is the steady state temperature at a point X and Y. So that will be depends on two independent variable of X and Y. Okay, so that when we have no heat source or no heat sink, so that this term on the right here can be equal to 0. Yeah. Okay, so that we will solve this using finite difference. Yeah. So if we have a plate, we will discretize into nodes here. We have the grid, or we give nodes for the point here. So that, for example, here we have in x direction, we have from the index is from 0 up to m plus 1. So it means that we have 6. We have 1, 2. So that will be m plus 1. Yeah, in which m is the number. Yeah. So that will be m is the interior node. Yeah, m is the interior node. And here we have n from in y direction, we have from 0 up to n plus 1. Okay, so if we solve this one, yeah, we assume the heat source is 0, so that we have this equation for the 2D heat conduction. Now we substitute the second derivative here with the central divided difference, in which this is second order accurate. Yeah, so that we have Ti plus 1j minus 2 Tij plus Ti minus 1j divided by delta x squared. Again, in y direction, the second derivative in y direction will be similar, but now we change the direction in j, yeah, and delta y. So that we substitute it in the equation here, so that here for the second derivative in x, so this is the equation, yeah. So the left one here is the second derivative in x, and this is the second derivative in y, so that will be equal to 0. If we assume that the distance or the interval size of the node is similar in x and y direction, or delta x is equal to delta y, so that this can be omitted, yeah, because it's similar. So that we can collect together the value of Ti plus 1, so that will be here, and we collect together the value of Ti minus 1j, so this will be it. And then we have Tij plus 1, yeah. And we have Tij minus 1, we collect together. And we have this one will be minus 4 Tij. And that is equals to 0. Yeah, so here we have a Laplace difference equation. And you can see that in general, yeah, the coefficient here, when we add together the coefficient here of the neighboring cell, that will be equals to the value here. Okay, so this equation holds for all interior points. It means that if we have 5 interior points, so that we have 5 equations like this one to be applied for each of the nodes. Okay, so we will see now example 29.1 in the book, in which we have a plate, yeah, a sheet of metal, heated sheet of metal, and the edges of the sheet are kept at constant temperature. So we have the top side here is kept at 100 degrees, the left one is 75, the right one is 50, and here the bottom is 0 degree. And this is steady state, yeah, steady state temperature. So it means that we don't have T variable in the equations. Okay, so that here we want to discretize the domain, so that here the sheet is divided to 5 by 5 grids. Yeah. So if we divide it into 5 by 5, yeah, it means that we have 5 nodes, yeah, here. So that if we have 5 by 5, it means we have 1, 2, 3, 4, 5, yeah, and in y direction as well, 1, 2, 3, 4, 5. But because we give a boundary conditions to all of the sides here, so it means that the boundary condition here means that we already apply a value here for the nodes. Yeah, so all of the nodes here will be 75 degree, and all of the nodes here will be 0 degree, and this one will be 50. Yeah, so that because the temperature here is already known, so that what we don't know yet is the temperature for the interior point here. Yeah, so that we give an index here in which the interior point will be from 1, 1 to 1, 3, 1, yeah, and up to 3, 3. So that here, because we have 5 by 5 grid, but we have the boundary nodes, so that the unknown will be 9 points, yeah, 9 nodes, which is the unknown temperature. So that means that we need 9 equations in order to solve the temperature for each of the point here, yeah, for 9 points. Okay, so in this case, we fix the temperature at the boundary, yeah, at a fixed value. So this means that we are using the Dirichlet boundary condition. So here we have the temperature defined. So when we talk about boundary condition, there are 2 types of boundary condition. Yeah. So the first one is called the Dirichlet boundary condition, and the second is called the Newman boundary condition. Yeah, so there are 2 types of boundary condition. The first one, which is Dirichlet. What is meant by Dirichlet? It means that we give a scalar value for the variable. Yeah, we give a scalar value for the variable itself. So for example, here we have the temperature. So it means that at this boundary, we give a temperature to a constant value, which is 50 degrees Celsius. So this means that this is the Dirichlet boundary condition. We give a value, which is explicitly the value of the temperature at that point, at that node is 50 degrees. When we have the Newman boundary condition, it means that what we specify is not the variable. Yeah, it's not the variable, but in Newman, what we specified is the gradient. Yeah, so that, for example, we applying dTdx is equals to 0. So this means that we applying a Newman boundary condition. Or for example, we have a dTdx, which is to a constant value, other value aside from 0. Or for example, we have convections to the surrounding, to the ambient air, for example. So that will be the gradient as well. So we can use that, and that will be the Newman boundary conditions. So when we have the Newman boundary condition, it means that what we give here is not the temperature, but what we give here is dTdx, yeah, to a certain value. For example, dTdx is 0. So it means that when we have this point has dTdx 0, it means that there is the temperature between this point and the other point here. Yeah. So for example, if we have another point, so that means the temperature will be the same. Yeah. So that means dTdx is 0. So dTdx 0 is 0 like this one. Yeah. So if we have temperature with x, if we have temperature with x, so dTdx 0 is like this one. Yeah, there is no change of temperature in x direction. No change of temperature in x direction. So what it means, so how if we applying the Newman boundary condition, so how can we calculate the temperature? So it means that we don't know the temperature yet, so this should be calculated as well. Yeah. So the information that we have at the boundary is the gradient with the Newman boundary condition. It means we also need to find the temperature, because the temperature is unknown yet. And how this temperature can be obtained is calculating from the domain inside. Yeah, when we have the temperature inside, so that we can calculate the temperature at the boundary. Yeah, so that this is in general. Yeah, so we have 2 types of boundary condition. So say back again in the problem that we have there before, all of the temperature is set on the sides. So that means that we have all Dirichlet boundary condition. So that now we can write the equation for each of the node. So for example, we take a node 1, comma 1, which is the first node here. Yeah. So then we insert the equations that we have before here. Yeah. Here we have this equation. So we're applying that for all of the nodes here. And for 1, comma 1, we have T21, yeah, plus T01 plus T12 plus T10 minus 4 times of T11. Yeah. So when we, for example, here we have T11. So that on the left here we have T01, and this one is T21, and the top one is T12, and the bottom one is T10. So that T21, the node on the right, plus the node on the left, plus the node on the south, yeah, on the top, plus the node at the bottom here, minus 4 times T11, which is the point itself, that will be equal to 0. And because this is the boundary in which we have 75 degree, and this at the bottom boundary we have 0, the temperature, so that we can insert the value already, yeah. So this will be the boundary point. So we insert the value here in the equations. So that this equation where the boundary condition applied now reduce into this equation. Okay, so we have one equation which is 4.11, and we need to find for the other 8 points. Yeah. Now we will see here again the same calculation. We can find for the top one here, which is T13. Yeah. So at these nodes, we can calculate that will be T03 plus T14 plus T12 plus T23 minus 4 times the point itself, which is T13, is equal to 0. And we have the boundary nodes here, which is T03, which is 75, and T14, which is 100 on the top boundary. So we can insert that. And now this can be moved to the right-hand side. Yeah, so this value, the boundary condition here will be the right-hand side. Again, now we continue to point 223. So similarly, that will be equals, that can be calculated with this equation. So T13 plus T24 plus T33 plus T22, all of the surrounding nodes, minus 4 times T23, that will be equals to 0. So that again, we have the boundary nodes, which is 100 here at T24. So we substitute that, and that moves to the right, becomes the right-hand side. So when we apply all of the nodes, yeah, be applying the equation for all of the interior nodes, so that we will have 9 unknowns. The temperature, yeah, at 9 points, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So 9 points. And we have the right-hand side here, which is obtained from the boundary condition actually. Yeah. So this value is a boundary condition, which is moved to the right-hand side because now it becomes constant value. And we see here that we have the coefficient matrix. So we see here that this is the coefficient for the point itself, which is ij. And this is the coefficient for the nodes on the east side or on the right side. So that will be I plus 1j. And this will be, so the value here, yeah, so this will be the coefficient matrix to the dependency to point I minus 1j. And this one on the top here, we have the coefficient of the dependency to point ij plus 1. Similarly, here at the bottom, we have point for ij minus 1, yeah, at the bottom, or the south node. So we see here that we have banded matrix. Yeah. So once we have these equations, yeah, and then we can calculate, yeah. We can solve these linear algebra equations with iterative method. Yeah, commonly when we have lots of nodes, lots of unknown, yeah, or lots of equations, so that we can use iterative methods such as Gauss-Seidel. So what you have learned in heat transfer is that you constructed this matrix, yeah, but you don't explicitly construct this matrix, but you directly use it using Gauss-Seidel method. So the method that is used in heat transfer is Gauss-Seidel, in which you rearrange the equations so that you can solve, for example, from the first equations to solve for T13, and then the second equation to solve T23, and so on. Yeah. So in Gauss-Seidel method, for example, this one, so that we can solve T13, so that will be equals to T12 plus T23 plus 175 over 4. Yeah, so that will be the calculation. So this is the equations, and we can do this iteratively. So we calculate using Gauss-Seidel method. Yeah, so this is what you have learned in heat transfer. So basically we constructed this, although depends on the solver, you might not explicitly write down the matrix as this one. So that when we look at this, we can extend further. Yeah, for example, if we have third order, we have 3D, for example, 3D heat conduction. So we can do the same as well. Yeah, when we have 3D heat conduction, so that we expect that there will be a value, the dependency to K as well. So that if we extend to 3-dimensional heat conduction, for example, on a cube, so that we will have K here. So that will be the dependency with K plus 1, and that will be the coefficient to the dependency to K minus 1 point. Yeah, so this will be the example. And please remember that this is second order accurate. Yeah, so the method here that we talk about is second order accurate. Why is second order accurate? Because we were using in the discretization before, we used the central divided difference, yeah, central divided difference, which is second order accurate, yeah, which is second order accurate. Now you can also, for example, apply higher order accurate scheme, for example, more than second order. For example, we want to apply fourth order central divided difference. So of course you can just substitute this one, yeah, the equation here, with the fourth order. Yeah, so if we have this one, so you can substitute this one with fourth order. So when you increase the level of the accuracy, so that you might need to include more neighboring cell. So when you use fourth order difference scheme, it might be that you need Ti plus 2 point and Ti minus 2. Yeah. So that this is for fourth order. So then you will have more dependency to the other points, so that when you use higher order scheme, it means that the coefficient matrix here that is constructed is not only Ti plus 1, but you will have a value here on the diagonal, which is the dependency, yeah, the coefficient of the dependency to I plus 2 and to I minus 2, for example, if you have higher order scheme. So it means that when we change this, when we change the scheme in the discretization, it means we change the coefficient matrix. Yeah. So we see that what constructed the coefficient matrix, yeah, the matrix A. So if we talk again about the solution of set of linear algebra, yeah. So this one. So in this PDA case, we can see that A here will change, yeah. A here will change, depends on the scheme that we use, whether this is forward or backward, or in this case, we are using central divided difference. For the case of elliptic, central divided difference is preferable. Yeah, it's preferable because it's quite stable and it gives quite good accuracy, which is second order. Yeah, for the basic central divided difference. So we can see here that the coefficient matrix A here is depends on the scheme, yeah, and also depends on the value of delta x and delta y, because we have seen before that the equation that we use here to construct the coefficient matrix, back again here in the basic. So the coefficient matrix here that is obtained, so the coefficient that is obtained here is because we're assuming that delta x is uniform and is similar to delta y. What if the value of delta x is not equal to delta y? It means that the coefficient matrix will change as well. Yeah. What if the sizing is not uniform? For example, from one point to the other point, delta x is not similar. It means that for each of the equation itself, the value of the coefficient will not be the same. So in this case, we have the same equations. Yeah, we have the same coefficient here for each of the row because it's a uniform sizing of delta x and also delta y. So we can see here that when we change the scheme, when we change delta x or delta y, it means that we change the coefficient matrix. And again, when we learn about a set of linear algebra before, we understand that how easy this matrix to be solved, how easy this system to be solved depends on the condition number of A. Yeah, on the condition number of A. So it means that when we change this value, it means that we change the condition number of A. And that also affected whether this system is easier to be solved or not. Yeah. And usually if we have a more complex scheme, yeah, if you have a more complex scheme, for example, higher order scheme, usually it becomes more complex so that the condition number increase. So that if you have a more a higher order scheme, usually the system is more difficult to be solved, yeah, or more difficult to get a low residual. For example, if you do the calculation in Gauss-Seidel, yeah, because we understand here that when we change this, yeah, when we change this value, so that we change the condition number or we change the coefficient matrix itself. Now, this is very important if you're interested later in simulation, like in FEM or CFD. So you will see the correlation between this, yeah. For example, the sizing of the grid, yeah, with how easy the system to be solved. Okay, so similarly, we can write it down as this one. So if we use Gauss-Seidel, we don't need to really construct explicitly the matrix, but we can write it down as this one. And then we can find, for example, we can solve T11 from the first equation and so on. Yeah, so using Gauss-Seidel. Okay, so that is about solving PDE. Any question?
Excuse me, ma'am.
Yes, Sultan.
I want to clarify something. So for the PDE is just only like we solve a two-dimensional probability transfer, right, ma'am, for the all condition.
Yeah, correct.
Oh, okay. Okay. And I want to ask something about assignment for last week. Last week you give us any assignment for problem 25.1, and on the classroom still don't have submission link, ma'am.
Oh yeah, I did give you an assignment. Yeah.
Yes, ma'am.
Okay. Yeah. All right. I will open it now. Thank you to remind me. That will be. Oh yeah, that will be the question from the slide. Yeah. Okay. I will create it now. Yeah, you can upload it. Wait. Okay, so you can upload it. What assignment is this? ODE, yeah. Okay, assignment ODE. Okay, so you can upload it up to 12. Okay, so you can upload it now. Yeah. Yeah, the link has been provided. Yeah, you can upload it. I will give you a couple of minutes to upload the assignment. Yeah, and actually, if you look in the book about PDE, yeah, aside from elliptic, there is also parabolic. But yeah, for this course, we don't discuss parabolic. Yeah, so we limit only on elliptic equation. Okay, so we will continue a bit. It's not much for today, actually, but we will also have a project for this year. So I will continue a bit before we talk about the project. Yeah. Okay. So yeah. Now that will be for the elliptic problem. Before we continue, is there any question?
Me not yet, ma'am.
All right. So this is similar to what you have done in heat transfer, yeah?
Hmm?
Yeah, so we will continue. So that when we have the temperature distribution already, so we can find for the secondary variables. Yeah. So for example, we want to calculate the heat flux. Yeah. So the heat flux in this is incorrect. This should be at xx and this should be xy. Yeah. The heat flux in x direction and the heat flux in y direction. So we know the heat flux here will be the first derivative, yeah, the heat flux will be the first derivative. So the heat flux can be calculated with minus kx in Ti plus 1j minus Ti minus 1j divided by 2 times delta x. So again, if we want to find the heat flux, which is the first derivative, so we substitute the first derivative with, again, the second order central difference scheme. Yeah, so that for central difference, we calculate the slope at point I. Yeah, so this should be the heat flux at point I. So the heat flux at point I will be calculated by Ti plus 1J minus Ti minus 1J over 2 times delta X. Yeah, so this will be dt over dx. Similarly, if we want to find the heat flux in y direction, so that we need to calculate the value of dt over dy. Yeah, dt over dy. So that this dt dy can also be approximated with the central divided difference, which is Tij plus 1 minus Tij minus 1 divided by 2 times delta y. So that the resultant for the heat flux, yeah, we know the heat flux will be a factor in which it will have the direction as well. So that the magnitude of the heat flux will be the square root of qx, which is squared, plus qy squared. Yeah, and the direction, which is the angle of the factor of theta, yeah, so that will be arcus tangent of qy over qx. Yeah. Okay, so this is to calculate the secondary variable. And if we applying the Newman boundary condition as before, so that means we applying the heat flux. So we will see here that we have a special treatment for the boundary. Yeah. When we have a boundary, yeah, when we have a boundary node, it means that the node is starting from the boundary to the interior point. Yeah. Now, if we have the heat flux, for example, so we have the heat flux defined here. Yeah. Again, if we have the heat flux is defined at this point at the boundary, so this is the boundary point, so that the heat flux will be calculated using as well the second order central difference scheme. Now, because this is located at the boundary, it means that the only point that is available is the interior point. So in this case, it means that we have to provide another point which is not really exist. So this is called the ghost node. Yeah. So this is called the ghost node. What is the ghost node? So this is it's not actually exist. It's just a ghost. Yeah. So it's not really exist. But we give this to help in the calculation. Yeah. So that if we have dt dx, del t del x provided at the boundary, so it means that with second order central difference, that can be approximated, yeah, approximately equal to T1j. So that if it is T0j, so that will be the gradient here will be equal to T1j minus T minus 1j, which is the ghost node, divided by the distance, which is 2 delta x. So that if we have here the calculation of T0j and we treat this as in the interior node, so the equation will be like this. So T1j plus the node on the left, which is the ghost node, T minus 1j plus the node at the top, T0j plus 1 plus the node at the bottom, T0j minus 1 minus 4 times of T0j, and this will be equal to 0. Yeah, so this, when we treat that as in the interior point. Now, because we have this slope defined, yeah, so this is as, for example, provided as a constant value, because we use Newman boundary condition, so that now we can substitute the value here, T minus 1j here, which is the ghost node, yeah, with the value which is obtained from the gradient here. So that when we take T minus 1j, so that will be equals to T1j minus that go up, yeah, minus 2 times delta x times the gradient, which is provided, yeah, as a boundary condition. Yeah. So that if we have this boundary condition, so that we can substitute T minus 1j here. So when we substitute it here, so that we now have 2 times T1j, because we have T1j and T1j here. So that will be 2 times T1j minus 2 delta x del T over del x, the gradient, which is the boundary condition, plus T0j plus 1, the top node, plus T0j minus 1, the bottom node, minus 4 times T0j. That will be equal to 0. So this is when we have the Newman boundary condition. So that now we have this equation applied to the boundary nodes. Yeah. So this is applied for the boundary nodes when we have the Newman boundary condition. Yeah. So that we can insert the value of the gradient. Yeah. Okay. So this is for Newman boundary condition. So we have discussed the use of Dirichlet boundary condition, which is straightforward because we have the value, so we can insert directly the value for the calculation in the interior points. But if we have the Newman boundary condition, so that we also need to calculate the value of the temperature here in the boundary node, so that we can use this equation. Okay. So yeah, so that will be for PDE, for elliptic equations. Any questions? Okay, if there is no questions, so we will look further here when in the book here, which is in chapter 8, PDE, elliptic equations. So we will look at a bit yeah, we will discuss a bit here. In which we have the irregular boundaries. Yeah. So when we have an irregular boundaries, so what we've seen before is when we have a plate, yeah, a plate in which, the distance is assumed to be uniform, either in x direction or in y direction. Yeah. But now we will see if, for example, we have irregular boundaries. Yeah. So this is the illustration. For example, we have a plate in which we have an irregular shape like a curve here at one of the corner here. Yeah. So that when we want to calculate this one, yeah, when we can to calculate the dependency, yeah, we want to construct the equations to linearize the PDE at this point, so that now we have to consider that the distance is changing. Yeah, so the distance is not uniform again. So here we have non-uniform. So the distance here will should be accounted. Yeah, should be accounted in the calculation. Yeah. So if, for example, here we have a uniform distance of delta x, yeah, uniform delta x, but at this point we have different length. So that will be alpha 1 delta x. And for the second here to the right, we have alpha 2 delta x, for example. So this means that the length on to the right and to the left and to the right nodes can be different, and also to the top and to the bottom. Yeah, so that we have alpha 1 and alpha 2, and we have beta 1 and beta 2, which is multiplied by the delta value. So that if we look at here, when we have a non-uniform sizing there, so that we can now calculate, yeah, for the first derivative. Yeah. So if we want to calculate the first derivative here, say here we want to give a dt dx at I minus 1i, which is that. So that will be tij minus ti minus 1j. So this is the gradient between I minus 1 and I. Yeah. So if we have a point of I, and we have I, so if we have here is I, and we have I minus 1. So this is the gradient between these 2 points. Yeah, the gradient between these 2 points. So that will be Tij minus Ti minus 1j divided by the distance, which is the distance will be alpha 1 delta x. Okay, so this is the gradient which is connect I minus 1 to I. So it means that this is a backward scheme, yeah, backward scheme. And here if we want to connect delta t, the gradient from I to I plus 1, it means that we use a forward approach here. So this is first order approach, yeah. So that we find it there. So that will be alpha delta x, yeah. Okay. So this is backward and forward, all first derivative, first order accurate. So that now if we want to find the second derivative, yeah, so we can find the second derivative by finding the derivative, yeah, of the first derivative. Yeah, we can find the second derivative from the derivative of the first derivative. So that the derivative of the first derivative will be d del t del x of I plus 1, yeah, the gradient which is counted from the forward scheme, minus the gradient which is calculated from the backward scheme, divided by the del x here, that will be the average, yeah, divided by the average delta x. So that will be alpha 1 delta x plus alpha 2 delta x divided by 2. So that if we rearrange this equation and we do substitutions for delta t delta x as what we have before, yeah. So this is the value of delta x from the backward scheme, and this is the value from the forward scheme. And then we collect again together the terms, yeah. We collect together the value of delta x here, yeah, so that it can goes out from this at the front. And so that now we have del t del squared, so the second derivative of del squared t del x squared, yeah, so this is the second derivative now calculated as this one, yeah. So this is the second derivative based on that calculation, yeah. And we can also do the same in y direction, yeah. So the second derivative in y direction becomes this one. So if we have this, yeah, if we have this, and then we insert that, substitute it to the equation that we have, yeah, the 2D heat conduction. Yeah, so that when we insert this, so this is the equation that we have. And then we can collect together the terms, yeah. We have, yeah, so this is, we have Tij, and we have Tij, and this one is Tij. So we can collect together the term of Tij. Now this is the neighboring nodes, yeah. So on the left, on the right, on the bottom, and on the top. Okay, so you can see the calculation here for the problem. Yeah, so you can read this in the book, in which we have the irregular boundary, but with the lower edge, yeah, is curved, has a curve, so that the distance will not be similar. Yeah, so we have the value here in which there is a difference in the distance for that two nodes. Yeah. Okay, so once we insert that in the equation, so then now we have the linear algebra, the linear equation shown as this one. And then the next is the same. You can combine with the other equations for the interior points, and then you can solve it for the set of linear algebra. So we can see here, yeah. So this is the result. So in which these terms comes into, yeah. So this will be for the first equation. Now the rest will be the same, yeah. So the rest are the interior nodes. So there is no changes there, yeah. Okay, so that we can solve for the temperature. Okay, so this is when we have an irregular boundary. Yeah. So in this case, you can play around. Yeah. You can imagine if you have a slightly complex shape. Yeah. For example, so you can find the distribution of the temperature. Okay. And also we can find the heat flux. So the heat flux, yeah, the heat flux can be calculated similar to what we learned just now. Yeah. So we can apply the second order first derivative to find the heat flux, yeah? And then we can find the direction by finding the resultant. All right. So that will be all for today. Any question?
Anum.
Yeah. Okay. And be careful when we have a curve boundary. Yeah. And we have a normal gradient. So when we have a normal gradient, a little bit more here. When we have a normal gradient, it means that this will be in normal direction. Yeah. So be careful with this. All right. So I think that will be, yeah, that will be all. Yeah. All right. So this will be the basis for all of the study, yeah, with simulation, including in finite element and CFD. Yeah. So the basis is there. Well, although there is a little bit of difference, yeah, what we learned here, what we have learned here is the finite difference method. Yeah, but when we learn about a structural, which is a finite element method, so it's a little bit different. Yeah, it's a little bit different because it will be divided into element. Yeah, so not as points or nodes as what we've seen here. Yeah, not as point or nodes. Yeah, so what we are solving here is as nodes or points. So it means that it's a little bit discrete, yes, because we only get the point here. Yeah. And what happened between the points here is not calculated. Yeah. We can find the gradient. Yeah. We can do interpolation, but this is treatment only as a point. So this is called finite difference approach. When you learn about finite element method, so it's almost similar, but we have an element. So this node will lies in the element. Yeah. When we learn about, when you later learn about, for example, CFD, computational fluid dynamics, is also similar, but the difference is that you are applying that in a control volume. Yeah, in a control volume. So that means that this node will lies into a volume. Yeah. So if we have a finite element, so this lies into the element. While we have a control CFD, it means that we treat this as a volume. Yeah, so we treat that as a volume. So what is the difference? Finite element and finite volume is almost similar. Yeah, we have a shape there. We have an element as well. But when we use finite volume in CFD, the difference is that we treat this volume as a control volume. Yeah. So that when we have a control volume, so I think you have to learn that in fluid mechanics as well. When we have a control volume, so we have a mass flow rate that goes in and goes out from the control volume, for example. So that we also need to calculate the mass flow that goes into the control volume and goes out from the control volume. So that is a different to what we have learned here. Yeah. So finite difference method here, what we have learned here, is the basis for all of the development or all of the improvement later in finite element and CFD. Okay, so yeah, I think that will be, yeah, as an overview, yeah, that will be an overview to why we need to learn this, yeah. All right. And because you have done this in heat transfer as well, yeah, we will have a project which is due next week, yeah, which is due next week. We have 40 students here. So I want you to make a group of 4, yeah, make a group of 4. And then uh, yeah. I want you to do some simulation. Yeah. Okay. So the project is doing a simulation with MATLAB. Yeah. And in this simulation, you need to create your own code. Yeah. Create your own code. So the project will. So this is for the project. Yeah. For the report. So you need to next week you need to upload the report. So one report for one group. Yeah, so only one report for one group. So for the group, the member, each of the member do not need to submit the report. Yeah, so only one representative. Yeah, but on the report you should write down the all the name of all the member. Yeah, and also the student number. So this will be the report guideline. Yeah. So what should be provided in the report? Yeah. So the first one here is problem description. Yeah. So this is an open case. It means that uh, we will find a case in which this case will be an elliptic problem. So first you have to make sure that this is an elliptic problem. Yeah. You can find any case, but make sure that is a case of an elliptic problem. Yeah. And write down in the report the problem description, the schematic, what is going to be analyzed. Yeah. And what is the dimension. Yeah. The shape. And also the boundary conditions or the initial condition that needs to be provided. And the number of nodes, for example, and what variations that you use. So when we talk about what variation, it means that you need to do at least two variation. Yeah, two variations, so that you will do a bit of analysis in which you will compare the result within the first variation and the two variation. And what will be the variation, that will be up to you. So you can choose, for example, using different boundary conditions, or for example, using different number of nodes. Yeah. Yeah, we wait one moment. Okay, so we will return here. Yeah, so the first one is problem description, and the second is state the PDE that is being solved. Yeah, so because this is an elliptic, yeah, so that should be elliptic. Yeah, PDE, the basic equation. So write down the basic equations. If you, for example, solve a heat transfer problem, so write down the heat conduction equation. So this equation will be based on the theory of the physics. Yeah, depends on the problem, and the discretization method being used. Yeah, so you can use first or second or higher order. You can use forward, backward, or central scheme. What we have discussed in this method in Laplace were central difference scheme because it's known to be stable, and high order accurate scheme. Yeah, for less calculation. Yeah, for all approximately the same floating points operation. Yeah, and the fourth is show the resulting linear algebra equations. Yeah, if you have a very large problem, a very large problem or many points, so you don't need to explicitly construct a matrix. Yeah, but at least you show the steps on the discretization so that you have the linear algebra. For example, you give an example for how to calculate the interior points, and then you give an example of how to calculate, for example, the boundary points, for example. Yeah, so make sure that you give an example for different equations that appear for the nodes. Yeah, because sometimes one equation is not sufficient to be used for all of the nodes. And then the fifth is the solver that is being used to solve the linear algebra equation. So state what solver being used. Are you using direct inversion, for example, or are you using Gauss-Seidel or Jacobian, for example? Yeah. And the sixth is show the results and do analysis on that. Yeah. So for the results, you do post-processing, plot the contour, the graph, yeah, and also do analysis on the comparison, because we have at least two variations. Yeah, at least two variations. You can do more, but at least minimum of two variations. So do analysis. So what is the difference? Yeah. For example, you're comparing the number of nodes, less number of nodes or more number of nodes. Or for example, you compare between the lower order scheme with the higher order scheme, for example. Yeah, and then give a conclusion and also attach the copy of the code. Yeah. So what will be the marking points here? So the mark will depends on these five criteria. The first one is the originality, which is the understanding of the problem and the code. And this should be original. And also problem complexity. Yeah, problem complexity, how complex it is. Of course, if you have a more complex, for example, discretization scheme, that will account for higher marking. And then correctness of discretization and the code. Yeah, whether you already translate the problem into the correct code. Yeah, and also post-processing and the report itself. Yeah, so because we have an originality here, it means that it is not allowable to have the same problem between one group to another group. Yeah, so please do a custom problem to your group. Yeah, each group consists of 4 students, so I think there are a lot of members to have a discussion, yeah, on what problem should be solved in this case. Okay, so I think that will be for the project. Yeah, so it will be due next week, and we will have a discussion on the project. So I would like to have several groups to present the result. Yeah, I would like to have several groups to present the result. Of course, if you present the result, that will be accounted for an activity, additional activity marking. Yeah. Okay. So because the limited time available next week, perhaps not all the groups can present it. Yeah, can present the results. So that probably only 4 or 5 groups. Yeah, probably half. So that, yeah, if you Yeah. But if you present it in the discussion, so that will be additional point for you. Okay, so I think this is for the project, and I will upload this as well, yeah, in Classroom, so that you can further download it and and have a read on it. Any question?
No, ma'am, from me.
Okay. Now, do you want me to divide the group, or do you want to choose your own member?
Choose by our own, ma'am.
Okay, you want to choose by hour. Okay. What about the others? You agree with that?
Yes, ma'am.
Yes,
Right.
ma'am.
Okay.
Yes, ma'am.
Okay, so you are free to choose your own member of the group. Yeah. Now, no more question for the project. Clear, yeah? All right. Okay, so I think that will be all for today. Yeah, so you can prepare from now because we have limited time, only 1 week. Yeah. So you can use the rest of the time to have discussion to, you might need to construct the group first, yeah, and then have a discussion as well with the member. Okay, so I think that will be all for today. Thank you for joining the class. I'll see you again next week with the presentation, yeah. So prepare for that. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.